So we've talked about waves, the traditional waves that we see crashing against the shore anytime we visit the ocean, but there are other waves that we need to mention, particularly tides. But before we get to tides, let's talk about some of these other ones. In general, these all have the characteristic that the wavelength, remember the distance from crest to crest or trough to trough, is so large that they are always feeling the bottom. So, for instance, if the L divided by 2, which takes you down to the wave base, is much, 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 much greater than the depth of the water, then it's going to feel the bottom continuously. So let's look at a few of these. So first of all, there's something called storm surge, and it's not really a wave. It's just one crest being pushed in front of a big storm. So every year during hurricane season, when we have storm after storm entering the Caribbean and the Gulf of Mexico and heading towards our southeastern coast, those giant storms are pushing huge bodies of water in front of them. So it's not really a wave with all those characteristics of waves that we talked about last time. It's different. So that's storm surge. There is something called a seiche, and for those of us that live near the Great Lakes, this is something that happens here, but also in other sort of enclosed basins like the Red Sea, the Gulf of California, etc. There is no amplitude in the center. This is very much like that playground standard, the teeter-totter or seesaw, depending on where you come from, what you call it. But the waves just rock back and forth from one side of the basin to the other, and in the central part, like the center part of the teeter-totter, it stays the same. And so it just goes up and down like that. And that will happen after a big storm front passes over the Great Lakes. So you'll have, and we'll probably be having it soon, a cold front, giant cold front coming down from the Arctic, whipping down across Canada, reaching the Great Lakes, and it starts this rocking process, this seiche back and forth. Of more importance, then, would be these things called tsunamis. And we'll talk about tsunamis again later in greater detail, but a tsunami, sometimes people call them tidal waves. They have nothing to do with the tides, but these are giant sea waves caused by a disturbance, an earthquake, an asteroid plopping down into the water, that kind of thing. And the wavelengths here will be 200 miles, 100 miles, huge. So the wave bases would be half that. See, still 50 miles, let's say. That's still reaching the bottom of the ocean. And these velocities, they can travel at huge, huge speeds. Again, we'll talk about tsunamis again later, but they're a very special type of wave caused by these disturbances. We also have internal waves. Then these waves are waves that aren't at the surface of the Earth, but they're at the surface, or they're at the region called the pycnocline, a density difference. And so the photograph above is at the Rock of Gibraltar, the Gibraltar Straits, where on the right side you see the Mediterranean Sea, to the north is Spain, to the south is Africa, and you'll have waves that kind of hit this area here, this highly stratified area of the Mediterranean Sea, and they'll cause a disturbance or an underwater wave. And these things can have huge wavelengths again and cause tremendous effects. So there have been cases where submarines, which are sort of cruising, at ease at great depths in the ocean, will suddenly be violently interacted with by these internal waves. And a couple of submarines have been lost. So this is another type of wave. That all waves don't have to be at the surface of the water. But the other waves that we need to talk about today are the tides. And a lot of people don't think of tides as waves, but if you view them as the high tide is the crest and the low tide is the trough, then these things have a wavelength of thousands of miles, because you'll have the high tide, one crest come in, and then the next crest doesn't come in for either half a day or a full day, depending on where you're at. So these are the tides. And the picture you're looking at is an area of Newfoundland in Canada that is famous, the Bay of Fundy, for its extreme tidal range. You see the size, the height of the docks that they have to build there, because when the tide is in, it reaches to the top of those things, and you see when the tide is out, it drains away the whole particular region. What causes the tides? Several things. So pretty much the gravity, attraction of the moon, the sun, and any other object with a mass, even a small little asteroid going by, there is a gravitational attraction between the two. But obviously, the biggest attraction is by the largest mass, which would be the sun. But the sun is 63 million miles away. The moon is a much smaller mass, but it is very, very close. So actually the moon has a greater attraction on it. And in the diagram you'll see here, this is just doesn't show the sun, but it has the moon-Earth system, and the water on planet Earth literally gets pulled as a bulge towards the moon. When it does that, there is an opposite flinging force on the other side, and so you create a high facing the moon, lows in between at 90 degrees between, and then another high on the other side. This is this wave, this crest and crest, that travels around the globe as the Earth moves in it. The Earth rotates underneath these bulges, and if we didn't have those pesky land masses in the way, we'd have a beautiful model pretty much like this cartoon is drawn. When you have land masses in the way, the high tide hits them, reaches them, there's all kinds of extra interactions, but the simplest model is just modeling Earth, moon, and sun orientations. So let's look at that. First of all, we can talk about the different types of tides, and we have these things that are called spring tides. They are when you have the highest highs and the lowest lows. If you've ever lived near a coastal area or visited for an extreme length of time, you know that not all high tides are exactly the same. Not all low tides are exactly the same. That over the course of a month, you'll have what is known as the spring tide. That's when the high tide reaches its highest, and it happens when the Earth and moon and sun are in this orientation. Notice there's the sun, there's the moon, the new moon, and the full moon, and they are all in a linear fashion so that the gravitational attraction is at its maximum. These are the highest tides. If we look at the neap tides, these are the lowest high tides and the highest low tides. So the water neither raises too high during the high tide nor goes too low during the low tide, and these happen at the first and quarter moon because the moon is pulling at about a 90-degree orientation to the direction that the sun is pulling. So the two forces have a subtractive interaction with each other. What does this do? Well, we have several different types of tides, and you need to get used to these type of diagrams. Time is the x-axis, so usually there's 0, 12, 24. There's the day, the full day, so 24 hours in a day. And then there is the feet, which is the range of the tide here. And if you look at a lot of places, this is the most common tide type, where there are two high tides about the same in every single day. So Boston, Massachusetts, a lot of you have been there and noticed that if this is the mean tidal line, that the low is pretty low, the low is low, but then you have two of these highs within that 24-hour period. And if you go to a place like Boston, a coastal area, they are very attuned to when the high tides and low tides are because of their fishing industries, things like that. And you can get all kinds of good apps for your phones now that tell you tide times anywhere you want in the world. There are also mixed semi-diurnal tides. Notice you also have 2 highs and 2 lows in that 24-hour period, but one of them is much higher than the other one. So this is due again to that pesky continental configuration thing. The land interferes to the point where it creates this situation. It's not just, you see this example is San Diego. It's not just that, oh, the Pacific has this, the Atlantic has the other. It has to do more with the coastline and the interaction of the water due to bathymetric considerations. And then there's also this type called a diurnal tide. And if you've been in the Gulf of Mexico, you have a situation where, given, again, that the fact that there's a unique bathymetry, these enclosed basins, you're only going to have one high tide and one low tide. And they typically aren't really huge tidal difference as well. So these are the diurnal tides. So you need to know these: semi-diurnal, mixed semi-diurnal, and diurnal tides, and in particular those diagrams. Few odds and ends about tides. There's also these things called tidal bores. I encourage you to Google these and just look at some videos of these on YouTube. These occur if you have tides moving in these extremely small basins. Basically small basins or river valleys. So you have tides that will move inland hundreds of miles, and surfers can ride these waves inland for hundreds of miles. So the Amazon River is it's one of the largest rivers on planet Earth as far as the amount of or volume of water that goes from the land into the ocean every day. But every once in a while there are situations where a tidal bore moves the water the other way. Not necessarily moving so much the water, but the energy flow the other way. Speaking of energy then, tidal energy is one of the optimistic possible ways in which we will generate energy in the future that is carbon neutral. If you have places, think about it. These are huge waves that move in and move out. That's a lot of energy. If you simply put a turbine in front of this water, it's going to turn it, generate electricity, and then it'll do it again as the tide goes the other way. And so there's all kinds of places around the globe where people have built, they look like dams or bridges, but they have these turbines mounted below them that, again, get spun around, turned, generate energy as the tide moves in, and then the reverse the other way. The trouble is, it'll work locally. Some places it'll be great. The Thames River in London, for instance, would be one of them. But it's never going to be our full solution. But it's just kind of an interesting little thing that our physics and geophysics friends have come up with this way to harness this largest of waves on planet Earth.